Thank you so much. It's a pleasure to be here with you today. I'd like to talk about some issues in high-performance computing, and I'll try to relate them to climate and weather prediction. So I'm Jack Dongarra. I'm from the University of Tennessee. I have a position at Oak Ridge National Laboratory, and I also work at the University of Manchester in the UK. So you know this story as well as I do. Traditional science and engineering have been driven by really two things for thousands of years. They've been driven by theory and experimentation. So theory is a paper and pencil kind of experiment that we do. Sometimes we implement that in a physical system, and that physical experiment perhaps helps with the theory and builds on the theory, maybe causing changes to occur in the theory, and those theories get pushed to the experiment. And sometimes it's too difficult to build the physical experiment. Sometimes it's too expensive to carry out something. Sometimes it's too slow. If we have two galaxies that are colliding, that's an experiment that we can't actually perform. We have to rely on some other means to understand what happens. And sometimes it's too dangerous to carry out the experiments. And in those cases, we rely on computer simulation. So computational science is this third pillar of scientific discovery. It augments the theory and the experimentation with simulation, and the simulation is done on high-performance computing equipment, on supercomputers, perhaps. So we have a changing world today. Computing pervades all aspects of society. It has a tremendous impact on e-commerce and business and research and development. We have companies like Apple, Samsung, and Google, which dominate the world of smartphones. These guys are designing their own silicon. They're not relying on commodity processors. They're going out and designing their own stuff. We have companies such as Google, Microsoft, Amazon, and Apple, which really dominate the NASDAQ. Each of those companies are greater than $1 trillion in terms of their capitalization. And not far behind are companies like Baidu, Alibaba, Tencent. And again, these companies are designing their own silicon. They're not relying on commodity processors to drive their industry. They're going through their own mechanisms to build silicon that meets their needs. So if we take a look at the traditional computing companies, which I've listed here in blue, those traditional computing companies in aggregate, adding them all together, have about only $1 trillion of capitalization. And these other companies, such as Amazon, Google, Microsoft, and Apple, each have $1 trillion or more in terms of their worth. There's one exception here, and that's NVIDIA, which has this over $1 trillion capitalization coming about mainly because of its products that are used in machine learning. So they have an incredible stake in terms of high-performance computing itself. So again, cloud vendors are designing their own processors today. We see that with Alibaba with their CIPUs. Amazon has their Gravitons, Google has their TPUs, and Microsoft has their own systems for doing their cloud services. Even car companies are getting into the act. So Tesla is designing their own silicon. Again, they're not using commodity processors. They're designing their own silicon that meets the needs that they have for the products that they're developing or the uses that they're making of it. In high-performance computing, we really have a monoculture in terms of the processors. If we look at the top 500 lists, so this is a list of the 500 fastest computers, and we've been doing this since 1993. So this is a list based on a benchmark. You run a benchmark on your machine, and if we look at the rate of execution that you achieve on this benchmark is looking at 64-bit floating point operations. So that's sort of one of the rules for running the benchmark is you have to use that level of accuracy. And back when we started, back in 1993, there were 65 systems on the list that used Intel processors, 65 systems that used Intel, and the rest of them came from companies like IBM, Cray, SGI, Thinking Machines, NEC, Fujitsu, and Hitachi. So a very small number of machines were based on Intel processors themselves. And then something happened. And what happened was we had the attack of the killer micros. So the x86 architecture became more powerful and was able to be put in place to design systems that had tremendous computing power. So if you take a look at that top 500 list, we went from just a few machines that had Intel and AMD processors to today, the top 500 list is dominated by that x86 architecture coming from Intel and from AMD. So we have this incredible situation where 97% of the top 500 machines are designed in terms of using that processor. So it's a commodity processor that's being put together to build our high-performance systems that are driving scientific simulation today. And those companies that started out in the early 90s, most of them have stopped producing high-performance computing equipment. The market wasn't big enough to sustain them, and they basically went out of the business of providing those high-performance systems itself. If we take a look at the accelerators that are used on our high-performance systems, the accelerator base started around 2011 with accelerators being used to augment the power of those computers. So we're going to take a commodity processor and put it next to a graphical processing unit to boost the performance that we can achieve. And today we see a large number of machines being built. In fact, when we take a look at the top 500 list today, the top 500 list has an aggregate performance level of about 5.2 exaflops, 5.2 times 10 to the 18 floating point operations. That's the sum of the 500 machines. The accelerators, the machines that have accelerators, account for 3.5 exaflops of that aggregate. So a tremendous amount of computing power coming about by the use of GPUs on our systems. So again, we have NVIDIA dominating the GPUs that are on these machines. The interconnects on our high-performance machines are driven by, again, another commodity. Ethernet or InfiniBand are the systems that are in practical use. 85% of the top 500 machines use that commodity interconnect to connect the processors together to get to a high-performance computing system. And Linux is everywhere. So Linux is on 100% of the machines that we have today. So our machines are driven by commodity things, commodity processors, commodity accelerators, commodity interconnect. And that's there because of the cost associated with putting that stuff together. And that has a consequence. And I'll talk about that consequence as we go on. So today our high-performance machines are designed around a chip. So we think about a microprocessor which has multiple cores, multiple processors on that chip. And we take that chip and we put it on a board. In fact, we put multiple chips like that on a computer board. And today we augment that with GPUs, those accelerators. So those accelerators sit next to the processor itself. It's offloaded. We offload the computation to that accelerator. We ask it to perform something at very high rates of execution, and then we collect the results back. That's the typical flow in which we use our machines today. So that chip is there to pass information to the accelerator. The accelerator does the work and passes it back to the chip, and then communication may take place after that as well. So we take that board that has those chips composed of commodity processors plus accelerators, and we stick them into a cabinet. We fill that cabinet up with those boards, connect them together with some kind of interconnect, and that becomes a basic component of our high-performance computing system. And then we take that cabinet and replicate it and fill up a room. So we fill up a room about the size of 2 tennis courts with those cabinets, and that becomes the supercomputer. So our high-performance computer systems are driven by those commodity processors, those commodity accelerators, plus the commodity interconnects to get high-performance computing. And that's true of the top machines that we have today. So our high-performance computing machines today that are being used to drive scientific simulation, that are being used to drive science, are based on distributed memory. They're using MPI to pass messages between the processors, and OpenMP to do things in a shared memory context within one of those nodes. The fastest machine today is a machine at Oak Ridge National Laboratory in Tennessee. It's a machine that's called Frontier, and it has a peak performance of 2 exaflops. So that's 2 times 10 to the 18 floating point operations per second, and those are 64-bit floating point operations. It has 8.8 million cores in this machine. So if you're going to use this machine at scale, you had better be ready to orchestrate a computation which has 8.8 million things running on that machine. And it's based on AMD processors. So it has an AMD CPU plus AMD GPUs connected together that make up what I'll call a node on this machine. The thing to recognize is that 98% of the performance is coming from the GPUs. So you had better be using the GPUs to get your computation done, otherwise your computational speed is going to be much, much reduced in that context. Our computers are heterogeneous. They use commodity processors and those GPUs to accelerate things. The other thing to note is that communication is very expensive on these machines. So that really is the thing that's going to drive the performance of our computations, is moving data around on these machines. It's not the floating point execution rate. That's basically free in some sense. It's the communication that costs. So there's this old notion, if we have 2 algorithms that basically do the same thing, and one algorithm does more computations, more floating point operations, we would assume that the one that did less floating point operations was going to run faster. But that's not true today, given the fact that communication is the most expensive thing that we see. So even algorithms which do more work, more floating point work, can actually run faster than the other algorithm based on that assumption. And today, our processors have the ability to do various levels of computation: 64-bit floating point, 32-bit floating point. Those have been standard for many years. Today, our processors and our GPUs can do 16-bit floating point arithmetic. There's a standard for that. And some of them can even do 8-bit floating point arithmetic. So 8 bits is the floating point representation. They do that very, very rapidly. And those lower precisions are being driven by machine learning, where we don't need as much precision in our computations to carry out the notion that of AI and machine learning. So our fastest computers are measured in an exaflop. So what's a flop? When I talk about a flop, I'm talking about 1 addition or multiplication. And in this context, I'm talking about 64-bit operands. So we're going to do a 64-bit floating point add or a multiply. That's 1 floating point operation. And an exaflop is 1 billion floating point operations per second. That's an incredible amount of computation. I gave a talk a few months ago. There was a reporter in the audience, and he heard me say 1 billion. He interviewed me afterwards, and he scribbled some notes. And when I read the article in the newspaper the next day, the article said 2 billion. This is not 2 billion. This is 1 billion floating point operations per second. So incredible rates. Think of it like this. If each person on Earth were to do 1 computation per second, each person on Earth get together to perform 1 computation per second, it would take about 4 years to do an exaflop, to do 10 to the 18 operations. And that's what this computer can do in 1 second. So tremendous amount of computational complexity. We have this list of the top 500, and it was started back in 1993. It was started by my colleague Hans Moyer and Eric Strohmeyer. Hans was a professor at Mannheim University. He had a list of the 500 fastest machines, and they were ranked by the theoretical peak performance. And I had a benchmark called the LINPACK benchmark, which ran the LINPACK program that solves a system of linear equations. That's what the LINPACK benchmark does. It solves AX equal B. It solves that for a dense matrix problem. And Hans said we should put our list together and call it the top 500. So that's what happened back in 1993. Horst Simon, pictured here, joined the group a few years later, And we had a benchmark list that basically performed this computation here, AX equal B, on a dense matrix problem. Fill up a matrix with numbers, an n by n matrix, do Gaussian elimination with partial pivoting, compute a solution in 64-bit precision, and that becomes the benchmark. We're going to look at the rate of execution. The rate of execution, as you change the size of the problem, the rate of execution goes up until it reaches an asymptotic point. And we're going to use that asymptotic point to give the performance for your computer. So do Gauss elimination with partial pivoting, 64-bit computations. I'm going to give you a matrix. I'm going to check to see that you got the right answer, and then we're going to enter your rate in the top 500 table if you qualify. So this is a snapshot, if you will, of supercomputing going back to 1993. So this red line here is charting the computer at position number 1. So today, the number 1 machine is at 1.19 exaflops. So that's the rate of execution that it solved that benchmark problem. The guy at the bottom of the list is here at 1.87 petaflops. So roughly 3 orders of magnitude less performance. And that's sort of the window for supercomputing, if you will. And we can go back and look to see how things happened back in 1993 when we started this. The fastest computer was about 60 gigaflops, so quite a bit different in terms of the performance. And you notice, I put some trend lines in here. You notice that there's this funny break that occurs here around 2008 or 2009. So you might ask, what causes that to happen? And a conjecture might be Moore's law. So Moore's law is slowing down, it's not ended. So the number of gates on a chip is not increasing at the same rate it has been over the past years, and that may cause some effect. Dennard scaling broke down, the ability to change the feature size in the same amount of area and keep the voltage constant. That broke down about 2008, 2009 because of voltage leakage, which causes the chip to heat up. So today our chips are frozen at roughly 3 gigahertz in terms of the speed they operate because of the breakdown of Moore's law. They consume about 100 watts at that rate of execution. So back when we started this list, the fastest computer was at Los Alamos National Lab. It was a 1,000 processor machine called the thinking machine. It was used to do nuclear weapons simulation. And today my laptop, the machine I usually use to give talks, I can run the benchmark, and the benchmark runs at 426 gigaflops. That's stunning. I have a computer that runs about 12 hours. I use it on an airplane. I throw it under my seat. I use it mainly, to be honest, to read email, running at 426 gigaflops. And that would have been faster than that machine at Los Alamos National Laboratory used for nuclear weapons simulation. So stunning changes have taken place in high-performance computing. This is a list of the top 10 machines. So I'm not going to go through the list, but the number 1 machine is at a Department of Energy laboratory. It's an open science laboratory. It's called Oak Ridge National Lab. The machine is called Frontier. It's a machine that's built by HPE. HPE is the integrator. So HPE doesn't make chips. What they do is they take parts and put them together in a box and sell that box. So HPE is the integrator in this case. They have AMD chips, AMD multi-core chips, plus AMD accelerators in this box. And it uses interconnect that's called Slingshot. It comes from Cray. Cray used to build supercomputers. It was acquired by a number of companies and ended up being a company that provides an interconnect for high-performance machines. That number 1 machine has 8.7 million cores. So again, if you're going to use this machine at scale, that's what you had better be prepared to do. And the benchmark on that machine at that scale runs at 1.19 exaflops. And that's 71% of the theoretical peak performance. So the theoretical peak performance is a paper and pencil calculation. What's the frequency? How many operations can you do per cycle? How many processors do you have? You multiply all that together, and you come up with the theoretical peak performance. So they ran at 71% of the theoretical peak, and the power consumption under load was around 22 megawatts. 22 megawatts. So what's a megawatt? I live in the state of Tennessee in the US, and at my home, if I use 1 megawatt over 1 year, I'll get a bill from the electric company for $1 million. So that's a megawatt year. So that machine cost about $22 million to turn it on for the year. The machine costs $600 million. That's just the hardware cost for the machine. So these are expensive investments that are made to help drive science. And this machine is used from time to time at scale to run very large problems to do its computation. And the last column here is looking at the efficiency. So that's gigaflops per watt. So you want that number to be as high as possible. And this machine is running about 52 gigaflops per watt. And you can scan down the list. The US has 5 machines in the top 10. Japan has 1, Finland, Italy has 1, and China has a couple of machines in the list. In this second column here, I've listed the machines, and in red are the machines that use accelerators. So 9 of the top 10 machines use some kind of accelerator, GPU, to boost the performance. The one machine that doesn't is the machine in Japan. It has an ARM processor, and it has vector extensions. So it gets its kick, let's say, out of using those vector extensions on that ARM processor that was specially designed for doing scientific computations. And if you scan this list here, you see it has one of the highest percentages of peak performance, 82%. So that's a machine that was designed really for doing scientific computation. They took care in the design of the architecture as well as the CPU, as well as the interconnect to get high performance. Where the other machines on the list are less in terms of the performance that we see on this benchmark, and they are built on commodity processors and commodity interconnects. So again, this is the #1 machine on the top 10 list going back to 1993. We can see how things have performed. We reached a teraflop back in 1997 with the machine at Sandia National Lab, a Department of Energy machine that was specially built for Sandia. About 11 years later, we achieved a petaflop, 3 orders of magnitude in performance at a machine at Los Alamos National Lab called Roadrunner. And another 14 years later, we got 3 orders of magnitude again at the machine at Oak Ridge National Laboratory. So it's taking longer to get to much higher levels of performance. In this case, 14 years to get 3 orders of magnitude in performance. And some of that's coming about because of Moore's law slowing down and the effects of Dennard scaling not being there. If we use that graph and do a projection, what we see is that in order to get 1 order of magnitude, a greater performance, it looks like it's going to take 8 years. So again, there's going to be a struggle to get to much higher levels of performance because some of the breakdowns. We need some kind of assist or some kind of boost that occurs in the architecture that helped, just like the GPU was a boost that gave us better potential performance on our machines. So today we think about doing simulations, and those simulations that we do on our high performance machines are not driven by dense matrix computations. They're driven by solving partial differential equations, and those partial differential equations, when discretized, lead to a sparse matrix problem that we have to solve. Again, it's AX equals B, but the matrix is sparse, so it's not dense. A dense matrix, the computational kernel is a matrix multiply. Matrix multiply does order n cubed operations, and it moves order n squared pieces of data. So remember I said that communication was the most expensive thing. So here we're doing a lot of computations for very little data movement with matrix multiply, but in this case, we're doing a sparse matrix operation. Sparse matrix operations are characterized by an iterative method that does a sparse data structure against a vector, multiplying those together, and that has a lot of data movement. So doing this kind of problem, we would expect to see much less performance in terms of the fraction of theoretical peak. So we have another benchmark. This benchmark is called HPCG. This is running the conjugate gradients algorithm on solving a sparse matrix problem. So doing a sparse matrix problem, a lot more data movement associated with it. We're modeling a three-dimensional problem. There's a 27-point stencil, which leads to a data structure which looks something like this data structure here, where we have these bands which have numbers in them, and the rest of the matrix is filled with zeros. So we want to solve that problem and look at the performance that we get from solving that problem. So this is the results of that benchmark. And we have a different characterization now. The number one machine is that machine from Japan called Fugaku. And the way to read this here is this column here is the benchmark doing the dense matrix computation, the LINPACK benchmark. And this column is what we see from doing this sparse matrix problem. So we see a lot less performance. And if we take a look at the fraction of peak performance, again, that's the fraction of theoretical peak, we're seeing a return of very little from the theoretical peak. The fastest machine here is getting around 3% of the theoretical peak. So that's our dirty little secret in some sense. The machines that we have today, we get very little return in terms of the theoretical peak performance for doing real applications. So most applications are returning less than 10%. This particular one, driven by a sparse matrix computation, is getting on the order of 3%. And if we take a look at the number one machine for the other benchmark, here we're getting less than 1%. We're getting 0.8% of the theoretical peak for solving this problem. And this is a problem that has had a significant amount of optimization going into it to achieve this rate of execution. So think of a car, and think of a car that has the potential to run at 250 kilometers per hour. And you're only getting back around 2 kilometers per hour out of it. You'd be pretty disappointed with that race car if you had that kind of performance associated with it. Okay, so today we have a number of things that are changing the course in which we do our scientific computations. Machine learning is certainly one of those things. It's helping to move us along in the direction. It's not solving the problem, but it's helping us to solve the problem is the way to look at that. And we see it done in climate, biology, materials, high energy physics. All of them are using it, and more of them today. Machine learning does matrix multiply. It's a dense matrix multiply is the computational kernel, but it's small matrix multiplies. And they can get away with short precision. So that's where the 16-bit arithmetic comes in and perhaps can help with that. And we see a number of companies that produce hardware in this space. So they're producing hardware that specializes in aspects of machine learning that are needed to get the problem generated, and they're producing hardware that can be used in this space to drive the computation along. Climate is an issue, of course. We talked about it before. Professor Chu gave us this definition that climate is the average weather, and climate is what you expect, weather is what you get. So climate and weather are interrelated, of course, and they depend on different scales of time and space. And it's a complicated scenario. It involves looking at the atmosphere, it involves looking at the landmass, it involves looking at the ocean, it involves looking at sea ice, and modeling all of those things together to try to understand where we are in terms of the climate itself. And that says that we're going to be solving some equations, some partial differential equations. We're going to be doing a discretization of the planet, and we're going to be driving it using those models that we have for various components of that. And that turns into, again, a mathematical equations that represent the physical characterization that we need for each of those discretized boxes in that model. We take those mathematical equations and turn them into a computer program, and then we run that program on our high-performance computing machine, and come up with some kind of solution to that. And that gives us something that we could perhaps see how well we're doing the modeling. We have some data that goes back for a number of years. We run the model and see how well it fits the model that we have. And that gives us an eye on trying to get the approximation and see how consistent the values that we have in the scenario are. And then we have different models that we can compare. So we get these ensembles that we can look at to give us a handle on what the climate really looks like. And we do that on our high-performance machines. So in the early days, in the 60s through the 90s, climate models were developed on scalar and vector computers. So things like the CDC 7600, which was a superscalar architecture, the Cray 1, which was a vector architecture, and a number of Cray machines existed in this time period. And then in the 90s, up until recently, the second stage was marked by looking at those killer microprocessors, putting together high-performance chips together, connecting them together, and using it as a machine, and building solutions based on that. So some of the early examples of a parallel global climate model used it, as well as a number of other models that were based on other systems. And today we're starting to see those models being adapted to heterogeneous architectures. We have the climate atmospheric model that's been run on the Chinese machine on the Sunway Tahoe Light. We have other models that have been run on other architectures, which I'll describe in a moment. And we see the use of high-performance machines as a step towards getting to basically kilometer-level climate modeling, and that's expected to reduce the uncertainty for many of these climate models. So here's sort of the state of the art, if you will, for some climate models run on a bunch of machines. So I went to the literature and looked at some of the results. So we have different climate models, 5 of them here. We have different machines that they've run on, different supercomputers in different countries that they've run on. And what we see is that the climate models are approaching around 5 kilometers or less in terms of the resolution that we see out of those climate models over time. And we get this figure of merit, this number of simulation days per day of computing, getting to roughly on the order of, in some of the best cases, around, we get 354, roughly 1 year of simulation days per day of computing. So we get basically 1 year of simulation per day of computing on these devices. And that varies, of course, depending on the model and what's expected from the model. And AI is playing an important role in our high-performance computing systems. Machine learning is being used in climate modeling. It's being used to detect events that are taking place. It's being used to fill in when we miss out certain pieces of data that's being collected. It's being used to help with the translation, the emulation, some of the prediction that we see from these climate models, and helping us with some of the parameterization that's needed to drive these models. If we take a look at what's expected, where we've been and what's expected to come in the future for climate models, the projection is that we'll get down to 1 kilometer resolution roughly in this time frame with new systems that are put in place and new models that are being developed. And ultimately, we want to be down to much less than that, of course. And the hope is that machine learning can help boost us so we don't have to wait as long to get to those points. And whether or not that actually happens has yet to be seen, but there is some hope that that's the case. Back in 1987, Gordon Bell, one of the computer architects, legendary computer architects, put up a prize. He was trying to promote using parallel applications. He was trying to promote applications that be run on parallel systems. So he was giving away $10,000 for the best application that beat the previous year's application running on a parallel machine. So we've had a long sequence of applications that have benefited from parallel processing. Gordon Bell has reached into his pocket and has given out $10,000 of his own money to that application that was judged to be the best. This year, he's pivoting and changing the Bell Prize to look at climate modeling. So he's giving away $10,000 for the best climate modeling application run on a parallel system. So today, there are 3 finalists in the Bell Climate Modeling Prize, and that prize is going to be given out next week at the big supercomputing meeting that'll be held in Denver. So these are the three finalists. This is a model that was developed at the Department of Energy laboratory. It's a large project. It involves 8 laboratories and a number of universities. It has about 50 FTEs associated with the project. It does atmospheric, land, ocean, ice model components, and it's a full-featured atmospheric global circulation model. And that project is getting resolution less than 3 kilometers in terms of the accuracy that it has, and it's one of the top rated ones. And again, it's giving us roughly 1 simulation year per day of computation, and that computation is run on a GPU-based system, getting high performance out of that ensemble. The other one that's in competition is actually related to weather, and this is a computation coming from Japan. It's a computation that was put together using the Japanese supercomputer. It was done during the Tokyo Olympics. They were concerned about heavy rainfall. So one of these microbursts that produces an incredible amount of rain in a very short period of time. So they had something like this occur back in 2008, where over 1 meter of rain came down in a 10-minute period of time, and the result of that was killing 5 people in Kobe, where the event occurred. So they wanted to monitor the weather to understand what was happening during the Olympics, and they put together a scenario where they were doing real-time data collection, feeding it into their supercomputer. They would get a 30-second refresh of the weather, numerical weather being pumped into their supercomputer. So every 30 seconds, basically 100 megabytes of radar sensing data was transferred over to the supercomputer. It was assembled on their high-performance computing system, and within 3 minutes, they had the forecast for the next 30 minutes. And they ended up doing 75,000 forecasts that were disseminated for the month-long period during the Olympics to help them understand what was happening. So that's the second one. That's the second finalist in the Gordon Bell Climate Prize. And the final one is a Chinese entry that was run on the Sunway Tahu Light System. It's using 40 million cores on that machine. It's running the Community Earth system model, a fully coupled model, giving us 3-kilometer resolution on that system, achieving super speed or a simulated speed of 340 simulation days per day of computation. So those are the finalists, and we'll find out next week who will come away with the $10,000 prize. Okay, so today we have this computing ecosystem, which is an enormous flux. We have great opportunities and challenges for advanced computing. Looking forward, it seems like it's increasingly unlikely that our future high-performance systems will be developed solely on commodity commercial parts. So we pay a tremendous penalty for using commodity parts in our supercomputing systems. That was seen by the fact that benchmark, we achieved less than 1% of the theoretical peak performance. That's coming about because of the slowness at which communication is done through those commodity parts. And if we had specialized parts, we could do much better. Advances are required to embrace this kind of end-to-end design of our systems. We have this notion of doing co-design. That's a mantra that we've talked about in the Department of Energy, but really we have very little co-design. Co-design is where we get the computer architects together with the algorithms people, together with the applications people, together with the software people to design a system that can meet the needs of the applications. And we're really not seeing that happen today. We take a look at some of the leading edge computing systems, and they're similar in some sense to our very specialized scientific instruments, like the Large Hadron Collider, like the gravitational wave detector, like the Square Kilometer Array. These are tremendous scientific instruments which are being used to push back the frontiers, that are designed on specialized hardware that can meet the needs without using the commodity processors that have been put in place. So I think I'll conclude with that as I'm being signaled that I'm out of time. So thank you very much for your attention, and I'd be happy to answer any questions.